Okay, now final stage is how we're going to find the minimum SOP. Once we finish the grouping, what will be the minimum SOP? So for this one, what we're going to do is from each group, we just keep the ones, okay, that participated in only one form, okay, complemented or uncomplemented. And the variables that participate in both forms in the group will be eliminated. So what does it mean? So let's look at this expression here. Okay, so let me erase the unnecessary parts. Okay, so let's focus on the table. We already did the grouping. Okay, so what do we have here is first 8-bit group, 4-bit group, and then the third group is with 2 bits. Okay, now what do we do is first let's analyze the variables in this first group. So we look at the variable A. Okay, A, it participated in 0 and 1 form, right? So if you look here, the A is 0. Sorry, A participated in one form only, right? 0, 0. So A is 0 here and 0 here, 0 here, 0 here, 0 here, 0 here, 0 here, 0 here. So A is always 0. If you look at this group, the value of the A is always 0, right? So we keep the A. But since it's a 0, we keep it in a complemented form. We keep the A complement, okay? Let's look at the B. B is changing from 0 to 1. So we eliminate the B. No more B. How about C and D? If you look, C and D is changing. C at the beginning is 0 and then it becomes 1. D is at the beginning 0 and it becomes 1. Right? So in this group, in this bit group, value of the C and D is changing and value of the B is changing. So we keep the A complement. So our original A complement, we keep it. Okay? Next 4-bit group. Look at this 4-bit group. Now, in this 4-bit group, we analyze this one. So from here we got the A complement. From this 4-bit group, if you look, value of the A is changing from 0 to 1, right? So in these 4 bits, A is changing from 0 to 1. So we eliminate the A. B is not changing. If you look in these the rows, B is always 1. Okay, so we keep the B. Since it's a 1, we keep it in a uncomplemented original form, B. Now let's look at the value of the C. C is 1, 1 here, right? So in this case, 1, 1. C is not changing, so we keep the value of the C. But D is changing. D is changing from the 1 to 0, so we eliminate the D. So we got the BC. This is our original term here, BC, A complement BC. Now let's look at the last group, the final group here. In this group, if you look from here to here, A is changing. A was 0 at the beginning, but here it's 1 now. So we eliminate the A. How about the B? B is not changing. B is 0 here and B is 0 here as well. So we keep the B, but since it's 0, we keep it as a complemented. How about the C and D? They are not changing, right? C and D is 0, 1. So we keep the C in a complemented form and D. So this will be our final term. So this expression here will be equal to, so this expression here is equal to A complement plus BC plus B complement, C complement, D. B complement, C complement, D. Okay? So we simplify the expression compared to this one. In this case, we have the last term had 4 variables. In our case, it has only 3 now. Okay, so this is simplification. Of course, not the best example of the simplification, but later we're going to see the more and more examples. Okay, now let's look at the next example here, right? So this is we already done the grouping. Okay, so in this case, we already did the grouping. So let's look at the example and analyze this. So what we're going to get from let's say from the big group. So when you have the large group with 8 bits, you will get the only single variable output. So the output from this group will be, what is it? So if you look at the A is changing from 0 to 1. So we drop the A, but B is not changing. B is 1 here, right? So we keep the B. So from this group, okay, let me get, from this group, we keep the value of the B, and that's it actually. Because we know that from the 8-bit group, there is only single variable, okay? So we keep the B. And if you look at the C and D, they're changing. Throughout this group, the C is at the beginning 0, and then it becomes 1. D is 0, and then it becomes 1 from the 0. So we keep the B here. How about this next group, the 4-bit group? From this one, what do we take? So if you look from here, So value of the A is not changing, right? So here A is 0 and below is A is 0. So we keep the A here, but we keep it as a complemented because it's 0. So we keep the A complement. Next, B is changing. B is changing from 0 to 1. We drop the B. How about C? C is not changing, so we keep the C. And D is changing from 1 to 0, so we drop the C. So from this group here, we got the A, C complement. And the final group here, we take the values of the A. A is not changing, right? So A is not changing. We keep the A here. B is changing. We drop the B. C and D is not changing, so we just keep the C complement and D. Okay, so indeed this is the answer. B, A complement C, A, C complement D. So these are the other examples. So we just look at the sum of them. The rest you can do on your own. I already give the answer here. You can see the answers. So for example, the last example here, we have the two groups here. The first big group, the 8-bit group. So from here, if you look, the A is changing, right? So A is always changing from 0 to 1, 1 to 4, and B is also changing. If you look at the C, the value of the C here is 0, and the value of the C here is 1. Only thing that is not changing is the D. D is 0 here, and D is 0 here. So we just keep the D complement because it's 0. We just take the D complement. From this group, let's analyze this group. So we have the A and B is changing. A is changing from 0 to 1. B is not changing. B is 1 here and B is 1 here. So we just keep the value of the B. And let's look at the C and D. So C is not changing, right? So it's not changing. D is changing. D is changing from 0 to 1. But C is always 0. So we just keep the C complement and so on. So by analyzing all of this, you can get the final expression. Okay, so the rule is that when you have the group, for example, when you do the grouping, right? So if you have the group with, let's say that we're talking about the cases when we have the 3 variables. So if you have the 3 variables, single bit group will produce the 3 variable term. If you have the 2-bit group, it will produce the 2-bit variable, a 2-bit term. And if you have the 4-bit, so like this here, the 4 bits in this case will produce the single variable term. Okay. Here, for example, if you have the group with 8 bits, it will produce the single variable term. If you have the group with 4 bits, like this one, it will produce the 2 variable term. So this is a slide explaining that one. Okay. So this is another example how we're gonna do the minimization. So this is our original expression, right? So A, B complement C, A complement B, C, A complement B complement C, etc. So first we do the mapping. So this is the mapping, and then we do the grouping, right? So we group the bits, and then we do the minimization. So from these 4 bits, if you look here, so we have the 1, A is 1, and then A is 0. So A is changing. But B here, if you look, B is 0 and B is 0 here. So B is not changing here. So we keep the value of the B, right? C is changing from 0 to 1, so we drop the C. How about this group? So this group here, if you look, the A is not changing. A is 0 here and 0 here, so we keep the A complement, right? So A we keep in a complemented form. So in this case also, we have to keep the B in a complemented form. Why? Because B is 0 here and B is 0 here, okay? So we got from this group, we got the A complement, and then we got the C, right? So C is not changing. C is always 1, so we keep the C. So our final expression will be this expression will be equal to B complement plus A complement C, right? So this long expression has been minimized to this smaller expression with only 2 terms and only 3 variables. And this is the minimization for this expression here. So we have the very big expression, right? So it's in a non-standard form. So we have to first do the numerical expansion. After we do the mapping and we do the grouping and we do the minimization, this term has been this expression has been simplified to this expression below. And we can do the actually mapping directly from the truth table. So let's say if you have the truth table, you don't have to go from the expression and then from the expression to the what the binary, and from the binary to the mapping. Instead of that, you can do directly from the truth table, you can go to the mapping, right? So this is the value 0, 0, 0, we put 1, 1, 0, 0, we put 1, 1, 1, 0, we put 1, and 1, 1, 1, we put 1. So these are the positions of the that outputs. Okay, so another example is SOP for the BCD, right? So if you remember the binary coded decimal, with binary coded decimal we have some values, invalid values. In case of the BCD, there are some invalid values. If you remember, we have the 6 invalid values. So in that case, that invalid values are called the don't care terms. So we just fill up these invalid values. So these are the invalid values in case of the BCD. So we just fill up them with x's. But the good thing about that is we can group them with 1s. So whenever you have the x, you can group the x with 1. Okay, so instead of doing the 2-bit group, you can do the 8-bit group here. Okay, so let's say you have the 1, 1 here, so you can do the 8-bit grouping. Okay, so this is the advantage of the BCD and the minimization. So instead of this expression, you're gonna get with don't cares. So with don't care values, you got this expression y equal to a plus BCD. That's it. Okay, and you can actually minimize this expression. The expression here, you can see the very long expression. This is for the 7-segment display. If you remember 7-segment display, in order to show the different values, you have to light up the different sectors, right? So this is the value of the A, how you're gonna light up the different values. So you can do the minimization, and after the expression, instead of this long expression, you can use this expression here, right? A plus C plus BD plus B complement, D complement, that's it.